So this is part 5, the last part of the chapter 6 electronic structure of atoms set of lecture videos. So in part 4, we learned about electron configurations, all the rules that you have to follow on where the electrons go in an atom. We learned how to draw the orbital diagrams, which are just the boxes with the arrows pointing up or down. The arrows represent electrons, the boxes represent the orbitals. And we talked about how to do condensed or noble gas electron configurations for the elements that have lots and lots and lots of electrons. Okay, so at the end of that, I mentioned that there are 28 elements that I promise you I will not ask about on our test or on the final anytime. And they're the 28 elements that are down in the F block, elements 58 through 71 and 90 through 103, because they don't follow our pattern. Okay. Well, there are two situations on the main block of the periodic table, so in the S and P and D chunk, where they don't follow the trend either, but they are very consistent about not following the trend. So there are two exceptions, basically. We're going to have to learn those two exceptions because we're going to need to know how to do electron configurations of the main group elements on the periodic table, so S's and P's and D's, basically the big chunk. So we're going to talk about those exceptions, and then what we haven't talked about yet either are ions. What happens if it's not a neutral atom? What has a different number of electrons? So that's what we're going to be doing in part 5, plus a little bit of vocab. So the anomalies, that's the exceptions. Okay. The anomalies, the exceptions, are in the D block, and there's just two groups, two columns in the D block, and we're going to, I'll write this down again later, but it's going to be group 6 and group 11 that are going to be our weirdos. Okay, they're the ones that are going to have the irregularities. Every other column on the periodic table, the electron configuration works exactly the way you'd expect. Like you just count your finger along and you'd get exactly what. So this is just showing part of the electron configuration, like the end of the electron configuration for each of these. But for this group, what we would expect would be 4s2, 3d, 1, 2, 3, 4. That's what we'd expect. I guess for chromium. And then for molybdenum, we'd expect 5s2, 4d4. Okay, but what it shows is that in real life, it does 4s1, 3d5. Now, if we count, 2 plus 4 equals 6. 5 plus 1 equals 6. So they have the same number of electrons. It's just that, what happened is one of the 4s electrons moved over to the 3ds. Okay. We see a very similar pattern happening over here. For copper, we would expect argon, and then 4s2, 3d9. If we counted, 1, 2 for the s's, 1, 2, 3, 4, 5, 6, 7, 8, 9 for the copper. What we see instead is 4s1, 3d10. Okay, so these are our two exceptions. And it follows for silver and gold also. It's just 5s1, 4d10, 6s1, 5d10 kind of thing. Okay. So this is just saying, writing that out. Group 6 is the first one. In group 6, what we see is the 1s electron move over to the d's. So there's still the same number of electrons, but this doesn't happen. This happens instead. And that's true for chromium, molybdenum, tungsten, and seaborgium. I don't really care about him, but okay, there. So those are the ones that are weird. It's group 6. Okay. The other one is group 11, which is copper, silver, gold, and I seriously don't care about this guy. So what they do is one electron goes from the S to the D. So this is all about energy and it's all about stability. So it turns out, the D or D block, D orbitals. Okay, so we're going to call that the 3 Ds. Okay. The Ds have 5 different orbitals. Those 5 shapes that I showed you back, I don't know which part now. 2 question mark with the 4 balloons tied together is what they look like in real life. 4 of them look like that, and 1 of them looked like this with a donut around the middle. Yeah, I shouldn't draw pictures. But so those are the 5 boxes. Okay, so chromium, if we counted it the normal way, would only have 4 electrons in the Ds. So that's almost halfway full. Okay, not quite, because it's missing 1. So that's why. So here would be the 4s. I really planned my space well here. And that's an S. There we go. That's why this buddy jumps on over here. So this 4s is left with, that didn't erase at all what I wanted it to, 1, and the 3 Ds are left with 5, which is a then half-filled set of orbitals. The Ds have 1 electron in each spot, so it's balanced. It's, balanced really is, I guess, the best kind of word. So it was actually worth it for the atom to use its own energy to throw this electron up in order for it to be balanced. I think on the next slide I'm going to have, no, there we go. There's the open space that I was looking for. Okay, so I'm going to look at copper, which is in group 11, which is one of the weird ones. Okay, so again, this is what we'd expect. We're going to write the electron configuration for copper. So if we do it the noble gas way, we'd start with argon. Then we'd say 4s2, 3d9, which if we draw the orbital diagram, and just so you know, when we draw orbital diagrams for elements that we use the noble gas configuration for, we're just going to draw the orbital diagram for the things that are after it. Otherwise, it would just take forever to draw all the boxes and arrows. 4, 5, 6, 7, 8, 9. There. Okay. And then what we get in real life is argon, 4s1, 3d10. So again, the difference, the 4s orbital only has 1 electron. And the 3ds, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's the 9 that were there above. But that 1 electron that left the 4s comes over here, the 3d, so it's completely full. So again, it's balanced. It was worth the energy. Copper itself had to use its own energy to pop this electron up and move it over there. Which again, seems weird. It's breaking the rules. The electron configuration rules. We have to fill up the thing that comes before we go to the next one. And so that's where the electron originally goes. But then copper uses its own energy to push it over here to the 3d orbital. And then it's actually more stable this way. Both ways, it has 1 unpaired electron. So it's not like it gained unpaired electrons or something. But this is what happens with group 11. Group 6, again, is the other. Oh my gosh. Group 6 is also a weirdo. Otherwise, everything else on the periodic table follows the trend. Okay. So, you do need to know those two, is what I'm saying. I could ask you copper, silver, gold, chromium, molybdenum, tungsten. Those are fair games in terms of asking you to do them on exams or any other time. Okay. So now we're going to talk about ions. We're also going to have to do a little bit of vocab, but ions are important here because ions are atoms that have gained or lost electrons, and we're talking about electron configuration. So what the heck happens when it gains or loses electrons? So first of all, when electrons are added or removed, they're always coming from the highest energy level, which again is the N value. So it's something like 4s. 4 is the energy level. Something like 2p. 2 is the energy level. So the energy level is the number out front. That's not always necessarily the last thing that you will have written down in the electron configuration, though, because like even the exceptions we just talked about, 4s1, 3d5, that's chromium. So of those two, 4 is the highest energy level because I'm comparing 4 to 3. So which number is bigger, 4 or 3? So 4. Okay. So if electrons are added or removed, it's going to come from the highest energy level first. So actually, even though 3s5 or 3d5, I'm sorry, is the last thing that I wrote down there, electrons are going to be added or removed from the 4s instead because it's a higher energy level. This only gets weird if it's one of the transition metals, if you end in one of the Ds. If you end as an S or a P, it's the last thing you write down and it's the highest energy level. Okay, so this is one of those weird ones. Here's the electron configuration for nickel when it's neutral. Down here, it's a 2+, which again means it lost 2 electrons. So it had to lose 2 electrons from the highest energy level. So we're comparing this to this. So 4 is bigger. So what I'm going to do is we have to remove 2 electrons. There just so happens to be 2 electrons right there. So those 2 electrons are now gone. The 3D was not touched. So we could, if we wanted to, write argon 4s0, 3d8. That is also correct. Okay. I'm going to do one that's not a noble gas, though. Let's do nitrogen. So its electron configuration when it's neutral, 1s2, 2s2, 2p3. Well, nitrogen, when it's an ion, it's in group 15, so it becomes a 3- charge. So 3-, that means it gained 3 electrons. So we're going to look at the electron configuration of nitrogen. So we're looking for the highest energy level. So energy level 1, energy level 2, energy level 2. So energy level 2 is the biggest. Now there are 2 of them, 2s and 2p. Well, if we look, 2s, so if we're gaining 3 electrons, we have to put 3 electrons somewhere. 3 electrons cannot fit in the 2s. 2s only holds 2 electrons, it's already full. So we're going to have to do this to the 2p. So what we're going to do is 1s2 and 2s2 are unchanged. 2p3, I'm going to add 3 more electrons to that, and the p orbital can hold 6, so 2p6. That's the electron configuration for the nitride ion, the nitrogen with a 3- charge. So if you're writing the electron configuration for an ion, pretty much write the electron configuration for the neutral atom, and then add or remove electrons as appropriate from the highest energy level. So from the thing that has the biggest number out front. You still can't break the rules, though. You can't put 8 electrons in a p orbital. P orbitals only hold 6. S orbitals only hold 2. So if something is full, like you have to add 6 electrons, but only 2 of them can fit into the p orbital, then you just have to keep going to the next step. You'd go on to the next s or whatever. So you're not going to see that. Most of the time, what ends up happening is these ions end up looking like noble gases. And we actually talked about that. It didn't make a lot of sense at the time. Okay, buddy. That when we figured out charges, like that sodium was a +1, magnesium was a +2, chlorine was a -1 based on their group, they added or lost electrons so that way they had the same number of electrons as a noble gas. It's literally so their electron configuration looks like a noble gas. So when we write the electron configuration for an ion, I'm just letting you know that if you start noticing a pattern where they all end up looking like a noble gas, good job, you're doing it right. Like, that's a good thing. Okay. So the last type of electron configurations we can have, we're still going to have some vocab at the end of this, but are excited states. So earlier in the chapter, we talked about emission spectra, which is when you run electricity through a glass tube of an element and it lets off light. When that happens, we were talking about this with the Bohr model of the atom. We said the electrons jumped from energy level like 1 to energy level 2, and then they relaxed back down. Okay, so we talked about that with the Bohr model of the atom, but that's what happens with the quantum mechanical model of the atom as well. It's just the pictures aren't as pretty. So there's a reason why we talked about emission spectrum with Bohr. Plus, that's what he used to base his whole model on stuff. Anyway, for that moment in time, when you run electricity through an element where the electron is jumped up to a higher energy level, that electron configuration is not the same as what it normally would be. Okay, so that's called the excited state electron configuration. What we have done, every single electron configuration before now are the ground state electron configuration. That just means, I'm going to say normal, that's not really fair, but it's relaxed, normal, what it's doing, nothing is weird happening. You just fill up the orbitals from bottom to top. Excited states of atoms, that's when energy has been added. And so the electrons have moved. They've moved up higher than where they normally would be. Now, good news. Good news is I'm never going to say, hey, phosphorus. It's in It's in its excited state electron configuration. What is that? You don't know. I don't know. It's the electron would move somewhere. We don't know. So the way we need to be aware of these is I'm going to give you an excited state electron configuration. So I'm saying, hey, here's an electron configuration of an element in the excited state. Which element is it? So it's going to go in that direction. The good news is when electrons move in an excited state electron configuration, no new electrons are added. So it didn't lose or gain any electrons. All you have to do to figure out what element it is count up the electrons and then match that number to the number on the periodic table. So, for example, this one right here, well, aluminum. So I'm giving you the answer up front. These are for aluminum. Normally, aluminum looks like neon 3s2, 3p1. That's the ground electron configuration. Okay, so then we run electricity through it. It goes from 3s1, 3p2. That looks weird. Okay, so all I gotta do to figure out what it is, I know I already told you it's aluminum, but here's how we can figure that out. We have to add up together the electrons. So neon has 10 electrons. I looked at the periodic table to figure that out. 3s1, there's 1 electron there. 3p2, there's 2 electrons there, so I get 13. So I look at the periodic table. What element is element number 13? Hey, it's aluminum. I looked down at the other example. Neon, 3s1, 3p1, 4s1. That looks super weird. I don't care. Neon, 10 electrons. 3s1 has 1 electron. 3p1 has 1 electron. 4s1 has 1 electron. I add those together, I get 13. Element 13 on the periodic table is aluminum. With excited state electron configurations, I'm only going to use neutral atoms. Like if I throw in an ion, like it has an extra electron or something, it would be impossible. So these are all going to be neutral atoms. So excited states, add together the electrons. Again, I'm not going to say, hey, what's the excited electron configuration for calcium? I'm going to say, here's an electron configuration. What element is it? That's how these are going to go. Okay. So let's practice this one. I want you to look at this, take a second, figure out what element you think it is. So what we want to be doing is adding together the electrons. So 2, nope. Okay. 2, 2, 6, 1, 3, 1. So 2 plus 2 plus 6 is 10, plus 1 plus 3, so 10, 11, plus 3 is 14, plus 1 is 15. So I'd look on the periodic table. Element 15 is phosphorus. Hey, we're geniuses. Okay, so that's how the questions are going to go with this. So I lost some vocab words somewhere. Oh no. Did I delete some slides? It's really not cool. Yep, I so did. Okay, so I don't know how I did this, but I apparently deleted something. So I've got a couple of words to add that I know are in your notes for chapter 6, but I somehow lost them. Where are they? They are, oh wait, maybe, sorry, I'm looking at my paper notes just to see where they are. They are somewhere. I promise they are. Oh, they were earlier. Actually, I think they were supposed to be at the end of the last video and I didn't do it. Okay, so I'm going to put it on here. Sorry. So here's some vocab words. Valence electrons. Valence electrons are the electrons in the highest energy level, which I mentioned when we were doing the ions. So core electrons, they're electrons in everything other than the highest energy level, so I'm going to say the rest of electrons. So, for example, let's look at this. Oh yeah, that's a bad one because it's an excited state one. I want to go back to, I have bad choices. We're going to come to here. Okay. So this is an electron configuration. Okay. The valence electrons are the electrons in the highest energy level. So what we need to do is look for the energy levels. There's an energy level 4, there's an energy level 3. So which energy level is bigger? Well, 4. So how many electrons are in the 4th energy level? 2. That's how we can figure out valence electrons. So aluminum, right here. This is what aluminum typically looks like. So we're looking for the biggest energy level. So that's a 3, and that's a 3. The reason why I'm not worried about neon is because neon came before this, which means I automatically know that it has a smaller energy level. Neon electron configuration is 1s2, 2s2, 2p6. So 1, 2, or 3. So I look at the 3rd energy level. Which one's bigger, 3 or 3? They're both 3, so that means I have to look at all of them. So what's the total number of electrons? Well, there's a 3s2 and a 3p1, 3 valence electrons. Okay. So this is a concept that is going to continue into Chapter 7, Chapter 8, and Chapter 9. So we will practice the valence electron, core electron thing more. But what we're going to do is we're going to practice a couple more examples here, kind of not just from, actually not really, most of it is not from this section, but just kind of Chapter 6 in general. So first, we need to write the electron configuration for chlorine. So what you're going to want is your periodic table in front of you. And I'm going to do it the long way. So I'm not, well, let's do it both ways. We'll do the long way, and then we'll do the noble gas way. So for chlorine, chlorine has 17 electrons. Starting at the beginning, 1s2, 2s2, 2p6, 3s2, 3p5. So I followed along with my finger on the periodic table. So that's the, I guess, the entire, the long way, the normal electron configuration. If I wanted to do noble gas, then I would find chlorine on the periodic table. I'd go to the row above it and find the noble gas there, which is neon. So that's where I put my finger. And then I'd start counting from there, which would be 3s2, 3p5. Okay. So the next question says, how many valence electrons does chlorine have? So valence electrons, those are the ones that are in the highest energy level. So if you want, we can look at the first electron configuration. The energy levels are 1, 2, 2, 3, 3. So the highest energy level, not 1, not 2, but it's going to be 3. So we're going to look at the electrons in things that start with 3. So it's 2 plus 5, so 7 valence electrons. If we look over here, it's still 3 is the highest energy level that I see, so 2 plus 5, I get 7. Okay, so the next one, write the 4 quantum numbers, N, L, Ml, and Ms, for the last valence electron in chlorine. So the last valence electron, so all 7 of these are valence electrons. The last one would be the last one that I wrote down in there, okay? So if you remember earlier, electron configurations are the shorthand way of saying where the electrons are. Orbital diagrams are the best way. They give you the most detail. So since this is getting pretty detailed, I'm actually going to take my electron configuration and I'm going to draw the orbital diagram. So I'm going to say 3s, 2, 3p, 5. 1, 2, 3, 4, 5. So it's asking for the last valence electron. So it's that buddy right there. Okay. So we have to write 4 quantum numbers about that electron. Okay, so N, energy level. Well, that electron is in the 3p orbital, so N is 3. L, that's the shape. So P is what's representing that, but there's a number that goes with that. S is 0, P is 1, D is 2, F is 3. So since this is a 3p, that's how I know it's a 1. I know in the 3rd energy level, there are s orbitals, there are p orbitals, and d orbitals. So L could be either 0 or 1 or 2. Well, in this specific situation, I know it's 1 because this is a 3p. So ML goes from -1 to +1. So this electron is in whichever one this is. So I would probably go with, oh my gosh, okay, 0. But actually, I would take any of those because we're not talking about how to know which one's the -1, which one's the 0, and which one's the +1. Remember, the MLs are the orientation, and that is the 3 different ways that p orbital is arranged in space. So we're not getting down to the specifics of that. The last one is MS, which is the spin, and this one is a down spin, so that's going to be a negative 1/2. Okay, so next. Same 3 questions, but for calcium. So first, the electron configuration for calcium. Again, I'm going to do it both ways. We're going to do long way, we're going to do noble gas, and we'll even go ahead and draw the orbital diagram. So long way, 1s2, 2s2, 2p6. Again, what I'm doing is I'm following my finger along until I run into calcium. 3s2, 3p6, 4s2. And that's where my finger hits calcium. So if I'm going to do the noble gas way, it would be argon 4s2. So when I'm going to draw the orbital diagram, I'm going to be super lazy, and I'm going to do it for this one, which means I'm just going to draw it for 4s2. So 4s1, 2. Okay. I could do it over here, but then I'd have to draw a box for the 1s, for the 2s, 3 boxes for the 3p, 1 for the 2p, sorry, 1 for the 3s, 3 for the 3p, and 1 for the 4s, which is fine. It's not that big of a deal, but I'm being super lazy. So the next question, how many valence electrons does calcium have? So we look at the electron configuration. We're looking at these numbers up front. 1, 2, 2, 3, 3, 4. We're looking for the biggest number. 4 is the biggest number. There are 2 electrons in that 4s, so it has 2 valence electrons. And then the next question is to write the 4 quantum numbers for the last valence electron in calcium. So it's the last electron that I wrote down, so it would be that, buddy. So N equals something, L equals something, ML equals something, MS equals something. So N, well, that's the number out front, so 4. L, well, the letter is S, so we have to remember what angular momentum quantum number goes with that, which is 0. Okay. ML, it goes from negative L to positive L. So negative 0 to positive 0, so I have 0. There's only one option for this one. MS is the spin, so that electron, the last electron that we wrote down, is pointing down, so I'm going to say negative 1/2. Okay. Let's do one more. For aluminum. Same deal. We're going to write the long way, the short way, we're going to draw the orbital diagram. So for aluminum, aluminum has 13 electrons, so 1s2, 2s2, 2p6, 3s2, 3p1. Now if I want to take aluminum and do the noble gas way, it looks like it'd be neon, 3s2, 3p1. So how many valence electrons does aluminum have? We're looking for the biggest energy level. 1, 2, 2, 3, 3. 3 is the biggest energy level, so we're going to look at everything in 3. So 2 electrons plus 1 electron, so 3 valence electrons. I guess what I haven't done yet is we haven't drawn the orbital diagram. So 3s, 3p, 3s2, 3p1. Okay. So write the 4 quantum numbers for the last valence electron on aluminum. So that's this buddy. So N equals something, L equals something, ML equals something, MS equals something. So N, we're looking at the electron on the 3p, so N is 3. L is, well, it's P, but we have to write a number for that, so that's 1. ML is either going to be -1, 0, or +1, and honestly, I would take any of those. Since it's the first box, I would say -1, but I'm going to say any. I would take any of those, okay? MS, that's the spin. Well, that electron happens to be pointing up, so I'm going to say +1/2. So the N value has to be 3 or it's wrong. The L value has to be 1 or it's wrong. The MS has to be +1/2 or it's wrong. For ML, as long as you gave me either -1, 0, or +1, you would be right, because I'm not making you know which box represents which one. Okay, so hopefully chapter 6 is coming together. Again, you want to make sure you've got a copy of your periodic table with you all the time, because you need it to write electron configurations. So good luck with everything, my friends. You can do this, and I'm sorry for my children. I'm sorry. So bye.